In the next two modules, we'll look at Appendix B1 and C of the book. You also have responsibility for other appendices identified in the chapters, and the content of those appendices will be found in the various chapters to which those appendices are attached. So in this, we're going to look at two modules. One is just interest rate terminology, which I think most people will be fairly familiar with. Effective annual rate means simply that if I invest $A at time 0, the value I have at time t measured in years is A times 1 plus r to the t. Continuously compounded means that the same $8 invested at a rate of r will accumulate at time t to A times e to the RT. So it's simply a way of moving money from time 0 to time t, or from time t to time 0. I would do the reciprocal of that multiplier function. And of course, if I were going from time little t to time t, the accumulation factor would be the familiar e to the r t minus t, and here it would be 1 plus r to the t minus t. Again, this is fairly elementary, certainly for actuarial students at your stage. The notion of equivalence simply means that if we have an annual and a continuous interest rate, we say they're equivalent if they accumulate investments to the same values. So obviously this does not depend on the dollar amount A, and at time t, if 1 plus RA to the t is equal to the exponential, and not only does the idea of equivalence not depend on the dollar amount invested A, it also doesn't depend on the time period t. Again, t is always in years, but it basically says that if two interest rates are equivalent over any period of time, they must be equivalent over every period of time. And we see just by doing a little bit of algebra that the annual and continuous rates are equivalent if they satisfy these familiar looking formulas. There's a generalization of annual which is commonplace. For example, semi-annual interest rates are common on bonds, as are monthly interest rates that are common on mortgage loans. And the general notion is one of an nthly nominal rate. And the basic idea is that time is always measured in years, and that we say that a rate Rn is an nthly nominal rate if, in order to accumulate cash from time 0 to time t years, we split each year into n parts, and we use 1/nth of the interest rate to accumulate over each part. So that instead of using the rate Rn, we use 1/nth of Rn as a rate, and we compound it over nt periods. So for example, if n was equal to 12 and I was dealing with a monthly nominal rate, and t was a 4-year, and I have an interest rate of, say, 6%, then to accumulate, this accumulation factor would be 1.005 raised to nt would be 48. So in a sense, the half of 1% is used per month. The equivalence idea extends to nominal rates, and if I wanted to know the equivalence of nominal rates and annual and continuous, I would just solve algebraically this. In addition, I can have the equivalence of two nominal rates, and a semi-annual and a monthly, for instance. Another interesting feature of the continuous rate is that numerically the notion of continuous compounding is really the limit of compounding over increasingly short periods. That if I fix a rate R, it's saying that the accumulation factor for a continuous rate of R is equal to the limit of what I get when I compound, treating R like an nthly nominal rate. So, and you can do this on your calculator. It's a simple exercise if you're not familiar with the mathematics of this limit. If you just take an R value of, say, 10%, and you calculate 1.1, and you calculate 1.05 squared, you calculate 1.025 to the fourth and 1.01 to the 10th. You won't have to, n will not get too far, too large, before you'll see that this is equivalent to e to the 0.10. Converges relatively quickly, and by the time you get to n well under 3 digits, you will have, in fact, by the time you get to something like 100, you'll get very good accuracy. So the conclusion is that continuous compounding can be thought of as approximately what happens when you use nominal compounding over a daily, or certainly if you did nominal compounding over an hourly, your calculations would be virtually identical to if you just assume continuous interest rates.